Alright, so for today's lesson we're going to be discussing implicit differentiation. Now the idea here is that y is some function of x. But here's the problem. It's unknown what that is. So f of x is unknown. Well, that's weird, because how am I taking a derivative if I don't know what it is? Exactly. So what we're going to do is we're going to say, well, y prime is dy dx. We're going to use that terminology. And we're going to algebraically solve for what this change is. Okay, and it's a lot easier than it sounds. So when we usually use this, we usually use it for a function that looks like this. Or something. The idea being here is that you, in order to solve this in graph, you'd have to do this: y equals, and then blah blah blah. You have to be able to solve for y, which you can't. So we say that y is an implicitly defined function. That is, it's not exactly a function from the standpoint of y as a function of x. It's implicit that it's a function of x. We understand it to be a function of x. Now, let's got the great googly moogly, and let's go to Desmos, and let's graph that sucker. Come on, you pig, let's go. Ta-da! Weird, Mr. Groom. I know, right? Well, what's interesting here is that when we do this problem, we could find the slope. And we could find it at any one of these points. So, for instance, right here, this point sure looks to be really close to right at 2, 0, or 2, 1, rather. It is. Yay! By the way, that's very unlikely that it'll be that nice, given the nastiness of the problem that I made up. So what we're going to do is this. We're going to take the derivative of this thing. And right here I see a product rule. It's a product because this right here is 2x times y. And it's also a function. Here I'm going to have to use a quotient rule. And then this thing here by itself. Now, here's the game. We know that y is some function of x. So, for instance, in the case of y squared, take the derivative of that. It's going to be 2y. Right? But y itself is a function of x. So I take the derivative of that, I need to do 2y times dy dx. In essence, what we're saying here is it's very similar to the chain rule. Okay, so last week, a couple weeks ago, we were doing things like this. You know, for instance, the cosine of 3x. Well, what's the derivative of cosine? Well, it's minus sine of 3x, of course, times the derivative of this inside function. It's a very similar procedure. The idea here is just be the negative sign of y times dy dx. Would be the only difference. The difference being I don't know what this function is, but I leave it in there, y, and then I plug it out here. I just go, well, times the derivative of the inside. So you get the hang of this. It's kind of fun after a while. It's not too horrible anyway. So the derivative of 2x is just 2 times the second function plus the first times the derivative of y. Well, it's dy dx. Minus the quotient rule, so it's the derivative of the top, so 6x times y, minus the top times the derivative of the bottom, all over the bottom squared. And now I want to rearrange. I'm going to clean this up a little bit, I guess. I want to get everything without a dy dx on the other side. So it's going to be 6xy and then everything on this side has a dy dx left over. So to solve for dy dx, I divide by that. So if I was interested in what happens at x equal 2, 1, I would literally plug it in. Well, we get 12 over 1 is 12. Minus 2 is 10 on top. And then it's 4 plus 12 is 16. Plus 16 is 32. So 5/16 of a slope. Well, does that look like it could have a slope of 5/16 right there? Yeah, I'd buy that for a nickel. In fact, if I wanted to, I could write y equals mx plus b. Here we go, this is 1, that's 2, and this is 5/16. So that's 5/8. So 3/8. So b is 3/8. So our answer could look something like this. Y equals 5/16 x plus 3/8. Nice, huh? Hey, that's hot. Alright, let's try another one here. Oh, we're gonna do this one here. It's not horrible. It's not bad either. Oops, not that one. Okay. Now, I could graph this in a minute. Of course, I could solve this one for y. That would be y is equal to plus or minus the square root of 16 minus x squared over 4, right? And you're like, that's great. The problem is you'd have to have two functions because y is squared. You have an upper function and a lower function, which suggests to me that in a minute we're going to see something like this. Notice it's not a true function of x because it does not pass the horizontal line test, the vertical line test. It doesn't have to be because this guy is not an explicit function, it's an implicit function. Remember, the difference being is back in the old days it was implied that people apparently had sex to have babies because, like on the old movies, the TV would go off. I mean, it would fade to black and then it would fade back up and then they've got 5 kids running around. You're like, how did that happen? It was implied what happened. They didn't go down and adopt them. But it was not really explicit on how that worked. Unfortunately, today's day and age, well, you know. Okay. So what's the derivative of 2x, or x squared? It's 2x. Notice that x is its own little function, so you don't take the derivative of anything but itself. However, here it's going to be 8y, and because y is a function of x, we multiply by dy dx is equal to 0, because the derivative of the constant is 0. Right, like that. Now, let's go take a look at this graph here real quick. Nice, huh? Hey, that's cute. So we are interested at some point. Now, for instance, by the way, notice that right here at this point, which is 4, 0, we better have an undefined slope, and we do. Nice. But Jay, what about Mr. Kroom? What happens at 0, 1? 0, 2 rather. I don't know. Let's see. At 0, too, you're going to get 0 over negative or whatever, and it's 0. Well, how about that? It's a 0 slope going across the top. Notice that in the first quadrant, they're all negative slopes. In the fourth quadrant, they're all positive slopes. And literally, it's a matter of plugging them in. Okay? This one here is pretty easy. Suppose x is equal to 1. Then you're going to get 1 plus 4y squared equals 16. So 15 divided by 4 is the square root of that. Mr. Grimm, what do you want? You want the positive one or the negative one? I don't know. Let's find out. .93. So if we went 1 comma 1.93, negative 1/8-ish of a slope. That's not too much. That's kind of cool. Okay, let's try another one here. Oh, that's hot. That's hot, yo. What? That's crazy, brah. Nice. Now, anywho, we can totally do the derivative of this guy. Any idiot can do it. So, the formula says, in the quote, x squared y Alright, so what's the derivative of this? Well, I need a product rule. So 2x times y plus x squared dy dx. Okay, now what's the derivative of cosine? Well, it's negative sine, so negative 3 sine of y. What's the derivative of y? It's dy dx equals 4, stupid. Now, if you bring everything without a dy dx to the other side, you will find that you'll end up with this guy. And so notice that at x equals 0, we've got 1, 2, 3, 4, 5, 6, 7. There's like a zillion of them, yo. So how many possible? There's a million. It's alright. You do the same thing with 5. You put 5 in, for instance. Notice that sometimes the computer will give you an actual value. Sometimes it'll tell you to blow out your ear. It's pretty close. If you put in 5 and 0.7, you'd have a pretty good idea for what, you know, the slope would be at that point. And literally it's just a matter of doing it from there on out. Okay. We will be doing some graphing on the Desmos. Just graph these guys. We can get as creative or as least creative. I mean, a lot of the stuff the computer's going to tell us what to do. The book, I mean, is going to tell us what to do. Oh, dude, you gotta be kidding me. That's pretty hot. I like that a lot. Man, it's all over the place, isn't it? Great. So, I'm not going to try to pick any particular point out. I mean, I could obviously put in 0, 0, I think. No, 0, 0 would be a problem, huh? But whatever. No, I don't want to leave this page. So, let's take a peek see at it here. So, cosine of 2x. Oh, it's 2x. So the derivative, now this is a quotient rule, or not quotient, a chain rule with a product inside. So the derivative of the outside function is negative sine 2xy times the derivative of the inside, which is 2y plus 2x dy dx, product rule, plus, now quotient here, so it's going to be 6 times y minus the top times the derivative of the bottom over the bottom squared equals, and then of course the derivative of that is just 3. Oops. So if you distribute this, you're going to get negative 2y sine 2xy plus minus 2x sine 2xy dy dx plus 6 over y minus 6x over y squared dy dx equals 3. Now again, move everything without a dy dx. Now, interesting. Are there places over here where you have vertical lines? Sure there are. Are there places where you have max and minimum? Sure looks like it. So we should probably have a 0 underneath that minimum right here, for instance. Right there should be a 0. And there should be another 0 right here, and so on. So I'm going to go ahead and graph my derivative and see what's up. What happened here? Okay, now it's interesting, right? What do you want to equal? You want to equal dy dx, but you can't really do that because we already have x's and y's here. So what you want to do is set it equal to some value. So I want to know where it equals 0. What? This equation has infinitely... Wow, yeah, that's pretty box office there, dude. So it's pretty interesting. What's going on here, I think, is the fact that... we're seeing negative slopes down in here. Obviously, these are all negative slopes. That's what's going on down in here. Then they jump up to positive slopes. I think that's because there's more of the function up here that we don't see all of it, the black function. I think we just ruined Desmos. Anyway, whatever. I don't really care anymore. Okay, so that one won't show up on your homework, obviously. This might, but the other won't. So yeah, so that's about all there is to this stuff. We could do a couple more here, I guess, just for fun. You could do something like 3x equals 2 over xy squared plus 4y cubed or something. So this is just going to be 3 equals, and then this, of course, this could be written a couple of different ways. Probably the easiest way would be to rewrite it as 2xy squared, y squared rather, to the minus 1, and treat it as a chain rule, because that's really what it is, but you can do it either way you want. Okay. Now, again, you could do it that way, or you could do it as a quotient rule. Either one would have worked. And so, if you do that, what you'll end up with is, again, let's just clean this up. This goes on the bottom. It's going to be -2. Alright, so what I'm going to do is something that we do in math pretty frequently. The big kids do anyway. Watch what I do here. Be amazed, yo. Okay, so let's add this thing to the other side. So you get 3 plus 2 y squared plus 2xy. Ta-da! Again, I would like to point out that our function dy dx is not a function of just x, it's a function of x and y both. Meaning when I want to go find the slope, I'm going to need to know not just an x coordinate, a y coordinate as well. So, good luck with that, and we'll see how you fare.